Thank you to everyone for coming to our July GSA WA Division talk. This month, we're really glad to have Axel Schmitt presenting for us. So Axel has, in the last 6 months, arrived at Curtin University and is running the new, very fancy new Kamika Sims that's been installed at the Laeter Centre. Thank you again for agreeing to speak with us about Zircon age spectroscopy and how the duration of Zircon crystallization can constrain pluton growth and hydrothermal longevity.
Okay.
Take it away.
Yeah. Thank you very much, Erin, for this nice introduction and the invitation to present here. So in the next 40 minutes or so, I hope I will not vent too much hot air and rather, clear the view on Zircon ages from a slightly different perspective than maybe most of you that you get Zircon ages here are probably pretty old. I will talk about Zircon ages on young time scales to give you some idea, what can be learned from that, and maybe also how that affects the way we think about ages for older rocks. So over the next half an hour, 40 minutes or so, I would like to address the following questions. One is a very philosophical one. What is actually a geological age? And the main point about it is sort of like, take your view from thinking about geological ages as dating events to more like dating geological processes that may actually happen over extended time periods. The second point is sort of like, how does Zircon form in natural environment, in its natural habitat, basically in a magmatic environment? And that's pretty much just a review of what is known. That's not necessarily my work. This is more like a compilation of sort of like what we know. And then the last point is sort of like just how can we use this information that we have to actually apply this and learn something that we may not be able to find out otherwise, mainly about the timescales of crustal magma accumulation. Before I do this, I would like to acknowledge a lot of people that were involved over the past couple of years in this project. Firstly, my current PhD student, Carlos. He's still at Heidelberg University, but he will come here to Perth to do analyses for his PhD here at Microprobe. And Henya, she was a master's student at Heidelberg University. She's now finished. And there are a whole lot of other collaborators in this project. And then, of course, this was funded originally by the Department of Energy in the United States, but then also by the German Research Foundation. And I would also like to mention the support of the geothermal industry that gave us access to the samples and provided logistical help and data.
Very quickly,
yeah.
The first time you had two back.
Sorry.
Was that New Zealand or something?
Oh, no, this is actually, this is California. I will talk about that. Yeah, so it looks pretty much like
geothermal industry.
Sorry?
You're talking about California.
California geothermal industry. Calpine is a US company, yeah. And, should have pointed that out. Okay. So what's a geological age? Typically, if we are users of geological ages, we sort of, we have our geological timeline, and we want to date, some event. Let's say a volcanic eruption that deposited a tephra, and then if we find this tephra, that tells us something about the depositional age. Or we can think about, a placement of a dike or a pluton. So like a point in time. However, a volcanic eruption or the placement of a pluton is the product of a long chain of events. So that we basically can look at all the precursor stages. So we have a timeline here, and this is a pseudo-logarithmic scale, so it's not linear. And we have certain processes that happen long before let's say a volcanic eruption, a volcanic event. If you talk about large-scale caldera eruptions, they typically happen in environments where we have long-lasting magmatic activity, like in a magmatic arc. And we know that magmatic arcs can have lifespans of many millions of years. Then we have, for example, for a caldera, a repose interval between big eruptions. It can be on the order of 100,000s to also millions of years. And so as we get closer to the eruption, we have processes that happen in the magma reservoir where we generate the bulk melt. We kind of have to cool that melt. We have to extract it. Often we may have a recharge event of hot melting magma from depth that reactivates the system, and that is the eruption trigger. And that may happen sort of from what we know about, looking at, for example, crystallization, that may happen, maybe thousands to hundreds of years before a big eruption. And finally, we get mixing in the magma reservoir and also in the column when the magma ascends to the surface. And then finally, that culminates in processes that may last over hours to days, where we have a big eruption. And then, of course, after the eruption, it's not over. We have essentially seismic events that may last. We know this from large eruptions that we observe for hours to days. We may have cooling of the volcanic deposits that have been erupted that may also last for days to months. And we may have climate effects after large eruptions that may even last for years or maybe even decades. With regard to human observation of all this chain of events that happens before and after an eruption, we only know a very, very limited amount of time. This is sort of like the human or the academic timescale, sort of the duration of a PhD, where we can directly look at these things. But often the history is much, much longer, and we need other tools. And I already mentioned we can look at crystals themselves and look at intracrystalline zonation, for example, and the diffusion. That will tell us something about processes that happen sort of like on timescales of hundreds to thousands of years. But then if we want to go further back in time, this is sort of where now this Zircon H spectroscopy comes in. We actually need these geological methods. Okay. This example was sort of for a volcanic eruption as a geological event. But I also would like to point out, like it could be also the emplacement of the magma. And this is just a little, already anticipation of the last part of the talk. These are flyers that the geothermal company made to inform the public of sort of what they're doing. And there's an old version and there's a new version. So essentially this geothermal field in California, but very similar to the geothermal systems in New Zealand. There is a steam reservoir that gets drilled. The steam gets extracted and put onto a turbine to generate electricity. And in the older version, you can sort of see, there's this magma pool underlying the steam field. The problem with that, this is wrong because there's no geophysical evidence that there is actually significant amount of melted material. And fortunately, when the newer version that I just downloaded in preparation for this talk, the company has been much more careful. They basically just say, okay, there is a magmatic heat from the Earth's interior that heats up that steam system. And of course, we want to know what is actually the heat source and what are the timescales over which these systems evolve and are active. Okay. So I mentioned already, Zircon is useful to tell us something about these timescales and these processes. And this is just a quick recap, why this is. Zircon by itself is a pretty boring mineral because it's just zirconium orthosilicate, but it can incorporate in its structure a lot of other trace elements. So the redder the color, the more the preference of zircon is for these elements. And the ones that are, of course, interesting from the geochronology perspective are thorium and uranium. And on the right-hand side, this is basically a short version of the decay chain in the uranium and thorium decay systems. That is just a reminder that we're not only having chronometers that are based on the ultimate parent and daughter, so uranium, thorium, and lead down here, but we also have intermediate steps. And these intermediate steps allow us also to use these as radioactive clocks. And the one system that I'm going to talk a little bit about here is the system that is involving 230 thorium. So that is the longest lived non-uranium intermediate daughter in the uranium decay chain. It has a half-life about 75,000 years. And so when we have disequilibrium in the decay system, we can detect this disequilibrium over timescales of sort of like 5 to 6 times the half-life of 230 thorium. So if it's 75,000 years, the half-life. So we can use this clock to about 300,000 years. So we talk about very, very young timescales in the quaternary. But then once we hit this limit where we establish secular equilibrium again, we can then use the familiar uranium lead system to actually date rocks. So Zircon is a good geochronometer, but it's not only that we have to have some radioactive elements that decays, but we also want to know what happens to these radioactive elements in the zircon crystal and what happens to the decay products. And this diagram is an Arrhenius type plot. It's a diffusion diagram where we have the logarithm of the diffusivity of different elements, uranium, thorium, and lead, against the inverse of time here. And the main point is, don't worry too much about these axes here. I mean, you can see that the temperature is centigrade up there. That's maybe a little bit more familiar. The main point is that diffusion of uranium, thorium, and lead in zircon is extremely slow. So if there are PhD students here or prospective PhD students, if somebody offers you a PhD on the diffusivity of uranium in zircon, back off. Don't take that because you will not measure anything in the time scales that are relevant. The experiments that have been done at very high temperature that are not really applicable to natural systems, and we sort of have to down extrapolate to more relevant temperatures, such as, let's say, 800 degrees. So even if you keep a zircon at 800 degrees, the lead, and especially the uranium and thorium in this zircon, will not go anywhere. It will migrate on the orders of nanometers to maybe tens of nanometers within the crystal. So a couple of atoms timescale. So not really something we can detect, maybe with the atom probe, but not with normal geochronology. Helium, tiny atom, that is a very fast diffuser. So just to remind you, we could also measure the production of helium in zircon. And that, of course, is a chronometer that tells us something about processes that happen at low temperature. It would essentially be an eruption geochronometer. But I will not really talk about helium here. We'll mostly talk about these uranium lead, uranium thorium systems. And then just the main point here is, okay, what we date is the crystallization. And even if the zircon is at high temperature in the magma, it doesn't care. It preserves that age information. And that now leads me to this term zircon spectrum or age spectrum. So what is it? What is the zircon age spectrum? And this is something we see more and more with increased analytical precision and improved analytical procedures. People that, let's say, date an off the run of the mill granite, you will find a range of ages. It's not sort of like a nice Gaussian distribution, and you take the average and think, okay, that's the age of that pluton. So, for example, in this case, this is a tertiary pluton from the Alps. This data from Schaldecker. 3 different hand samples. Each H bar represents the uncertainty of a single zircon measurement. And you can see that in this plutonic hand sample, the ages between these individual zircons vary by several 100,000 of years for this tertiary pluton. This would be sort of the absolute age here in millions of years. Okay. So this is what I would call a zircon age spectrum. So now some of you could say, well, what about lead loss? What about zircon inheritance? These are TIMS, thermal ionization mass spectrometry data, where the whole zircon is dissolved, and we measure, the uranium and lead and calculate the age from that. What if there was, a tiny bit of a xenocrystic core? Okay, that would make the age older. That's one possibility. We cannot completely rule that out. But overall, in this pluton, xenocrysts are very, very rare. Authors have only found 2 in, let's say, 100 zircons that they dated. What about lead loss? Okay, zircon can become metamixed, and then lead may be transported out of the crystal, and so our ages get reset to younger ages. But then these are, the state-of-the-art chemical aberration, isotope dilution TIMS ages, where actually all the potentially damaged part of the zircon gets dissolved by immersing the zircon in acids. Okay, so the TIMS people will tell you, no, we did everything to sort of avoid this lead loss. But you could still be skeptical. Okay, it's always good. But now here's, now a different time scale. These are data from a caldera in Central America. The volcano is called Ilopango. Ilopango had several eruptions. The last one was about 500 Common Era, sort of like 1,500 years ago. You can sort of see the age here. There are a couple older eruptions. So this this vertical bar is always the eruption age and the uncertainty. And then we have the zircon ages, but this time, this is not uranium lead, that's uranium thorium. Okay. So look at the scale here. This is also not millions of years. Now we have Ka, so thousands of years. So even for these volcanic rocks, the hand samples of the volcanic rock, we find zircons that are close to the eruption age. They overlap with an era, but they're always older than the eruption age. And the bulk of the population is much older than the eruption age by several 100,000 years. And this cannot be explained by lead loss because we don't measure lead here. This is uranium and thorium. And I already showed you uranium and thorium. These are the slowest diffusing elements in zircon that are sort of known. It doesn't, cannot explain this by any lead loss. You can see that some of these ages, once they get to this infinity symbol here, that essentially means they are in secular equilibrium. So we can't really say anything about their age, except for that they're older than 300,000 years. But we can go back with the ion microprobe and then analyze these grains again with the uranium lead method. And so now you see a subset of the data that we just showed before, sort of like lumping all the samples together because there were not that many of these older crystals. And now we look at the crystallization age uranium lead. And then also here, the eruption age is very young, close to 0. But we see that these zircon interiors are significantly older by about up to 2 million years. Okay. And that kind of correlates with the eruptive history of that caldera. That caldera had previous eruptions, and we can sort of see with these vertical bars that some of these eruptions go back to close to 2 million years. So again, this is evidence for protracted zircon crystallization in these systems. And these zircon age spectra, we cannot explain them away by some analytical method. This is a real signal. It's independent of the method that we use. So after this brief introduction, like what is a zircon age, what is a geological age, and what are zircon age spectra, I would like to now go one step back and sort of review a little bit of what we actually know where zircon form in magmas and how. So we have this very simplified, and this is clearly oversimplified system, where we have some melt production in the mantle. These are mafic melts. There's typically no zircon here. Very few zircons in the mantle. It's not that they're not there. Kimberlite sometimes have zircon, but these are sort of the oddballs. Most basalts will not have zircon. Even intermediate rocks, so as the magma ascends, it evolves, it differentiates, it becomes more silicious. Even these intermediate systems are typically zircon-free, zircon-bearing, and only when we get to an evolved stage, This is sort of where we form zircon. Doesn't necessarily have to be up here, depending on where our magma evolves. It could be anywhere within the continental crust. And what we know very well is, how zircon forms as a function of the melt composition, intermediate or evolved, and temperature. This is well calibrated for at least important melt composition, subalkaline melts. We also know pretty well how fast zirconium diffuses in a melt, how fast the zircon can actually crystallize. The kinetics of zircon crystallization are well constrained experimentally. What we don't really know is all the dynamics of this magma transport through the crust or through the lithosphere. That's very tricky. We have very strong viscosity contrast. A lot of these aspects, what happens, how do these different magma benches interact, how do they mix? That's still something of a black box. We don't know that. Okay. And also, how much of the material that is here that may contain zircon is actually that erupted at the surface. So just to show you now in an animation, how this calibration of zircon saturation in the melt works. This is a little animation of how I can get started. Okay, sorry, I have to probably go out here and start this first. Okay, so now we have sort of like a little animation going. This is a model calculation. If we take an intermediate melt, with sort of like dacite 65-8%, and we let it cool, how does the melt composition change and what happens to the zirconium in the melt? So not unsurprisingly, you sort of see temperature goes down, silica content goes up until we sort of get a minimum composition, and that's sort of like our most evolved melt. What happens to the zirconium in the same melt as we sort of cool? Zirconium is incompatible. So as long as we crystallize plage, CPX, amphibole, zirconium will go up, and only when we reach saturation, the zirconium concentration goes down. So this is the important point, exactly here, when zircon starts to crystallize. And that's the amount of zircon that crystallized. And so if we imagine this now sort of like one zircon crystal starts crystallizing, as we reach saturation, how does the zircon grow? We will sort of see that, initially we grow a lot of zircon, and then we add lesser and lesser amounts of zircon. There is, of course, a geometry effect here. This is a three-dimensional object, so any of these rims contains actually a large volume of the zircon. So this is why they, in a cross section to the zircon, become fairly small, these domains. But overall, the saturation conditions tell us that initially a lot of zircon crystallizes, and then as the temperature goes lower, because of the lower solubility of zirconium in these melts, the amount of zircon that crystallizes will also get less. Okay, so we know this very well. We have the experiments to do this, and now we can think about a magma system. And this is a very, very simple scenario where we have a batch of magma, a spherical geometry of magma that sits in the crust and that cools. Okay, so we sort of have a thermal gradient. The outside is cold, the inside is hot. This diagram, we don't care about the geothermal gradient, so this is a very unrealistic scenario. But nonetheless, we can sort of then look at, how much zircon will crystallize in each of these shells of our model magma chamber. So if we look at the outer part that cools fast, we will basically get, this amount of zircon until it solidifies. The inner part will take longer, so we will get essentially a more protracted crystallization of zircon. So if we then in the end sum up all the zircons that have formed in this volume sphere, we would expect a distribution that sort of looks like this. A lot of zircons that are old, and then fewer and fewer that are young. This is what this very, very simple scenario would predict. But however, this scenario is very unrealistic because we know that natural magma systems are not just one batch of magma that cools. but rather these magmatic systems have a protracted lifespan. They get rejuvenated due to magma recharge. You know, most volcanoes, most stratovolcanoes do not only erupt once, they have a million-year lifespan with multiple eruptions. So how does now the Zircon H spectrum look like for a system where we have multiple magma pulses that sort of come in one after the other? So each individual magma pulse will cool. This is sort of shown here. It's the cooling curve for the first batch of magma. But then we have a new batch of magma coming in before the old batch of magma has completely cooled and solidified. And then the third batch after that. So this is the same effect as, you know, if you're sitting in your bathtub, relaxing, you know, at some point the water gets cold, you have to either get out of the bathtub, the pleasure is over, or you crank up the heat. You know, you turn up the faucet and you let hot water in. So that's how you can basically maintain a warm temperature for a longer time. So basically here we have multiple magmatic events, and the average temperature sort of can remain high, can even increase depending on the temperature of the recharge, until we stop the magma recharge, and then everything starts cooling down. So how does the Zircon distribution now look if we basically add up all these Zircons? So basically what we see is, as long as we have magma recharge, the amount of Zircon increases, the younger Zircons, relative to the older ones. We have a distribution that looks something like that. It's actually the opposite of what we would have if we had a single magma system. These are very, very basic, simple scenarios, but they should serve to sort of make the point that there is information about the timescales and the volumes involved, the recharge rates of magma in a Zircon H distribution. Sort of this total H range that's represented here corresponds to the total duration over which we have magmatic activity, we have magma recharge, but also the shape tells us something about this magma recharge system. So here's now I'm getting a little beyond the everything else where I showed you. This is well established in the experiment. You know, Zircon saturation very well. Now it gets a little bit more murky. You know, how does actually realistically a magma chamber look like? And there's sort of these two end-member models. You can imagine many other sketches sort of in between, but this is sort of what the geophysicists love. This is sort of like a sill model where you have, you know, a volcano and you have maybe a geologic boundary here, where you have magma coming in, it forms a flat sill. And then the next batch of magma comes in and it forms another sill, sits underneath, and you build up gradually a magma system in the crust. The other end member is shown here. This is more the geochemical view of magma systems. So we have country rock and we have a bleb of magma that gets rejuvenated, recharged. And the recharged magma basically goes in the center of the magma body where it's the hottest, and it mixes well. And then we sort of have this from the inside out growing magma model. There's some important thermal consequences between these two end member models. So here, essentially, we always, when we have a high, we have a high surface to volume ratio with these flat sills. So that means they cool relatively fast compared to this sort of more spherical geometry, which has a low surface to volume ratio. And the other effect is, you know, here we always get the new magma in contact with cold country rock. So this is a very efficient way of losing heat for magma. Whereas here, the new magma always goes in the hottest part of the magma body, and there the heat loss is less efficient. So these are sort of end members, and you know, the truth is probably somewhere in between. The good news is our understanding of thermal diffusivity of magmas and rocks is also fairly well established. And we can essentially model, you know, any of these geometries quite well. this is a comparison between sort of this geophysical model, this pancake model, where we have still out the sill replacing for 1.1 million years, basically filling up this magma body here with a recharge rate of 9.1, 10 to the minus 6 cubic kilometers per year per square kilometer. And that would be the resulting magma chamber. The black line would be the solidus temperature. So everything that is inside that black line would be molten, would be magma. On the right-hand side, you can see with the same recharge rate, sort of this other end member model, where you can see this is the magma, the red dashed line is sort of the total intruded volume. Again, we have the solidus temperature here. This would be the molten magma body. And of course, it's bigger here and it's hotter, just for the reasons that I explained. What you can also see if you look closely in this diagram is there's sort of like a vertical line here that separates the left and the right part of the model. The same on the right-hand side. And you can see they're not exactly symmetric. There's a slight difference. This slight difference comes from a test that we did where we had different codes that model this heat loss in a magma system. This is a code that was developed at the University of Geneva. And on the right-hand side, you basically have another code that uses the same input parameters and just looks, okay, well, how does this magma body evolve? That was developed at Mainz University. And even though there are subtle differences, the good news is both models pretty much agree. And the same on the right-hand side for this spherical or ellipsoidal magma chamber. This is the UCLA Heidelberg code and then the Mainz code. And again, both agree. Okay. So after all this, hope I didn't cause too much confusion and you start losing trust in your Zircon ages. But I want to make the next step and basically show you in this case study that it's not only a nuisance that we have this protracted Zircon crystallization, but we can actually use this information to get some insight into magmatic processes. So what can we learn from this Zircon age spectrum? And now this is again this picture that I showed earlier. So we're going now to Northern California. This is the Geysers geothermal field. It started out as a health spa in the 1920s and 30s. And then starting in the 1950s, it was developed for geothermal energy uses. Just very briefly, so to hone you in where we're located. So this is the Western North American plate margin in a reconstruction, sort of like 40 million years ago. And if I start this animation, we can sort of see, the big geological event is change of a convergent plate boundary destruction to a transform boundary. So this is basically the San Andreas, and we have this triple junction here. Here, north of it, we still have subduction. And then south of it, we basically have a slab window. Subduction has ceased. And into this slab gap, hot atmospheric mantle material rises. And that causes melting. And these melts rise into the crust, and they melt the crust. And so we get a magma system that essentially migrates along with the migration of the Mendocino triple junction. So there's a range of volcanic systems that are between 15 and 0 million years, and only the youngest one is shown on the right-hand side on this map. The purple units below, this is so-called Sonoma volcanic field. That is an older phase, and the brownish colors, along with this red dashed area, that is the younger, the currently active volcanic field. That includes this geothermal field, the geysers. So I have to run that again. So it's a geothermal anomaly. So heat flow, surface heat flow is elevated by 5 to 10 times continental crustal average. The hottest part is in this red region there. And there are I don't know exactly how many geothermal power plants. I think the total installed capacity is 1 gigawatt. So that is enough electricity to basically provide electricity for the city of San Francisco, 725,000 homes, according to the website of Calpine, the operator. So what is the heat source of this geothermal system? There is volcanism at the surface. This is this pinkish purplish colors, which says Cobb Mountain. You know, these are volcanic rocks. They are about 1.2 million years old. If anybody of you deals with argon, actually one of the argon's reference materials is from this location, the so-called Alder Creek rhyolite. That's what's going on at the surface. We have these volcanic rocks, but there is also a subsurface pluton. You know, it's not exposed at the surface, but it's been drilled by hundreds of geothermal drill wells, and therefore its depth distribution can be reconstructed very reliably, and it's pretty much between about a kilometer depth to about 4 kilometer depth. That's the known extent of this pluton. Just to give you an idea how it looks like in this 3D reconstruction, sort of like an inverted boat, like a keel shape. And there's also some petrological differences. The shallowest part, this is this orange part here, this is called microgranite porphyry. And then the lower part is compositionally slightly different. I'll talk a little bit about that. But it's mostly also evolved compositions, granitic and granodiorite. So if we look at the zircon ages from the volcanic and the plutonic unit, you can see they again, there is a zircon age spectrum here. There's a range of ages. The shallowest part of the pluton is the oldest. It's between 2 and 1.5 million years. The deeper part is younger, so between maybe 1 to 1.5. And in the volcanic rocks, they actually have very similar ages compared to what we see at the depth. So this is a volcanic plutonic system. You can correlate the volcanic rocks with the plutonic rocks, and they also have a lot of other similarities, as I will show you in these diagrams. These are now trace element data for zircon. And I should mention, these rocks, especially the plutonic rocks, are highly altered. Now, this is an active geothermal field. They're pretty much at 350 degrees when they get drilled. So green schist, facies, metamorphic rocks that are affected by high degrees of fluid flow. So a lot of the original magmatic phases are altered and changed, but zircon is robust, and that's why zircon trace elements are important, just to tell you something about the magma composition and the origins. So the main point here is, there is a range of compositions. The oldest part of this pluton, this oldest and shallow part of the pluton, this microgranite, is actually more evolved than the deeper parts. You can see that at the high hafnium and the low europium star value. So this reflects how much plagioclase crystallization we had. The lower this number, the more differentiated the melt is. And the same with hafnium. The higher the hafnium concentration, the more previous zircon crystallization the melt has experienced. So that is mirrored by the titanium in zircon, which is a thermometer. So the lower the titanium in the zircon, the lower the temperature. So again, the shallow part of the pluton crystallized at very close to the granitic minimum temperatures, whereas the older, deeper part crystallized at somewhat higher temperatures. We also have hafnium and oxygen isotopes for the zircons. So that tells us something about the magma origins. And the main point here is these are hybrid magmas. So they are isotopically between a basaltic end member, which you can see sort of on the upper left here, and the country rock of this pluton, which is Greybacky, consistent formation. And we have a mixing, assimilation, fractional crystallization origin of these melts, of these plutonic rocks. Interestingly, even though that shallow older part was more evolved, it is isotopically actually identical to the bulk of the deeper, younger part of the Pluton. There is a sort of like an appendix here of slightly isotopically more evolved, more crustally contaminated zircons, but they are only found in the youngest volcanic and plutonic rocks. Okay. So zircon not only gives us an age, it gives us some information about the origin of the melt. But the main point that we now want to do is, can we use this zircon age spectroscopy method, so looking at the range of ages of zircon, to say something about the magma evolution? And that's sort of shown here. First of all, for the shallow older part of the Pluton, where we have a cumulative probability curve. So essentially, we just take the ages and we sort them in increasing age and stack them. So that's a ranked order plot. And that's identical to a cumulative probability diagram. And then we can try to model, how much magma recharge do we have, and when does the recharge have to begin in order to match this distribution? And as we can see is, for example, the red line would be a slightly higher recharge rate. If we have too much recharge, essentially, our system gets too big, and then when we turn off the magma supply, we crystallize a lot of zircon in a relatively short time. So this would be this curve, and that would be shorter and younger than what our actual ages are. So we have to then tweak the recharge rate and the onset of magma recharge until we get a distribution, and it's shown here in this gray line, that is close to the data. And we can do that also for the younger part of the intrusion. And the important thing is, you can already see this here, this is a much longer time scale. We talk about 300,000 years of zircon crystallization, whereas here on this axis, most of the zircon crystallizes within 150,000 years. So there is clearly some difference, and that is reflected then also in the different recharge rates. And the best fit for our data is again for this intermediate recharge rate, sort of like about 4 cubic kilometers per 1,000 years. So my student, Carlos, he ran a lot of different models, and this is the end product. So what he found is the best fit for the model with regard to the data. And you can sort of see the model curves here in these upper diagrams, for the shallow older part and the deeper younger part of the Pluton. And in order to get this distribution, we basically must have a system that initially was just boiling at a very, very low flame initially. So if we look here, this is the recharge rate. The recharge rate was sort of like 0.1 cubic kilometers for a long time. Okay, that allows us to crystallize zircon for a long time, but also zircon over a protracted amount of time. Then something happens. Okay, so we have a jump in the recharge rate. And then over a very, very short time, we have a lot of magma coming in. And that pretty much builds the bulk of the Pluton. So in about 50,000 years, we generate most of the Pluton. The total volume is sort of here. So we intrude on the order of 200 cubic kilometers in a very narrow time window. And then this big batch of magma starts cooling, and it produces zircon. And that's basically what gives us this curve here. In the end, he cranks up the zircon, the recharge rate again a little bit to sort of get this tail here. So yeah, that's a model. All models are wrong. Some are useful. So how can we look at this model and what can we learn from that? So first of all, there is actually some geological evidence that sort of also is consistent with this model. And this is indicated here. Within this geothermal field, pretty much above the Pluton, we have some small basaltic andesitic eruptions. And they happened at around 1.6 to 1.7 million years ago. If we already had a big volume of silicic melt at depth, these basalts would not come through that volume of melt. That's a density barrier. They would rather stall and mix with that melt than coming up to the surface without contamination. So in that regard, this evidence for these mafic eruptions is consistent with the absence of a large volume of a silicic intrusion at the time. And that's sort of what is also then in our model, completely independent, only based on the Zircon ages, where we sort of have to have this big recharge event at around 1.6 million years ago. So if we now take this together, what I showed you before, so that this is the known extent of Pluton, our Zircon model predicts that there is a total volume of around 300 cubic kilometers. What is known from the drilling, the known extent of this plutonic body is about 75 cubic kilometers. So that means, if we subtract 75 from 300, we have a residual intrusion that is sort of at depth of around 200 cubic kilometers. That's our hypothesis. When we say, okay, underneath the zone Pluton, there must be at least twice as much of this intruded volume at this relatively shallow level. So in the model we intrude is about 6 to 7 kilometers. Okay, this is still too small and too old to be the heat source for the present field. Even such a relatively large magma volume would cool relatively rapidly, and after a few 100,000 years, it should be at ambient temperature. All this, as I said, happened about 1 million years ago, and therefore, we can also conclude that there has to be more magma recharge to drive the modern geothermal system. That's still a big enigma. Nobody has really found the evidence for these young eruptions. There's nothing on the surface, but that is one conclusion from this model. We can't. This is sort of the limit of the volume of the magmas of this intrusive system, and so we can't postulate that it was much bigger because that would not be consistent with our data. But we cannot rule out that there is small volume recharge going on. Is there any other geologic evidence that would support such a scenario? A long, low-level activity that then suddenly spikes and then maybe goes back to a low-level activity. In the case of the California Coast Range volcanism, I mentioned that there are these older fields. It's actually quite interesting that in the precursor field of the current volcanic field, the Sonoma volcanics, there have been several large volume eruptions that distributed tephra over a large area. You can see one of these units, the Lawler Tuff, pretty much covered all the state of California. And there were 2 other large eruptions in a system that has a long activity range. So the overall activity of this field was between 8 and 2.5 million years. But all these big eruptions that produced tephra that is distributed over a wide range happened in a very brief period. They're dated by argon, and they're sort of between 4.8 and 4.6. So it seems like that this scenario of this spike, may not be unique to the geysers, but we may see something similar in these precursor fields. So with this, I would like to thank you for your attention. I hope I could show you that this Zircon age heterogeneity, even in a simple igneous rock, a volcanic rock, a plutonic rock, where we have different ages ranging tens to hundreds of thousands of years, is the rule rather than the exception. And that, of course, places some limit on the uncertainties that we can actually get from a Zircon age, especially if it's bulk Zircon age, we just the entire Zircon. The positive news is, this is a new tool to learn more about the actual conditions of Zircon crystallization, and it tells us something maybe about the size of plutons that we otherwise wouldn't be able to easily get to. Okay, so thank you very much.
Does anyone have any questions for Axel?
Yeah, no, that's an absolutely wonderful talk. So when you produce these age distributions, is that from this analyzing the surface, like the outside surface of a bunch of different zircons, or I guess what I'm leading to is, can you do a core to rim traverse to see?
Yes, that's a good question. Thank you. The data that is shown are actually they're different types of data. So often it's just basically all what I showed you about the geysers. These are section zircon where we just do one point in the middle of the crystal. That's very conventional. The example from the Central American volcano, the Lopango caldera, there we actually took a zircon without polishing and we drilled into the outermost rim. Oh, and let me show you this actually. I have a slide on that. So like a depth profile. And this is one of these examples where we actually take the zircon and we drill into the rim without polishing. And this is now, okay, this is a disequilibrium diagram. So this is how we read the age in the uranium thorium space. And we can see that the zircon rims, this is the outermost part in this profile, they are pretty much at 0. And as we drill in, we get between 2.9 and 4.2 microns. We are sort of at about 200,000 years. And then if we go even deeper, then we are at secular equilibrium. So this inner part of the zircon, so only this outermost rim here that is a little brighter is quaternary in age, and the rest is older. So yes, we can actually do, even for individual zircon, this type of depth profiling, and look at the age heterogeneity within a single crystal. Yeah.
What you're showing is mapping out recharge and eruption episodes from the age spectra of the zircons. Can you go back to the zircons that relate to a particular episode, go back to some of the other geochemical aspects of them, and tell us what may have triggered or may have been involved in those particular episodes?
Yes, that's also, a very good point. With regard to eruption trigger, it is probably very difficult because zircon crystallization and diffusion is very sluggish. So if you had the magma recharge event, the zircon may not see it, or at most the outermost part may be a little bit resorbed. The tips get rounded and things like that. That could be sort of related to the direct recharge that may happen very shortly before eruption. What we often see, and that's sort of see it a little bit in this diagram here. I hope it's not getting too arm wavy, but you can see in this diagram, this is again in Lopango, Central America, a lot of the zircons crystallize here. There's a peak here, and that's also a time when we have a lot of eruptions, and we can combine this age information with, let's say, temperature compositional information and compare, the erupted material from that time with the zircon that crystallized there. And often we see that there is the system becomes hotter during these episodes of multiple eruptions, and also where then a lot of zircon crystallizes from the residual melt that did not erupt. I hope that answered the question here.
You treated the thermal consequences as a direct product of magnetism, but then ended up with saying, well, there's sort of hot springs and that's a driver. What about the consequences of geothermal gradients, metamorphic fluids, and hydrothermal processes that are not directly related to the magma?
So the general idea about the geysers, is that there is a magnetic heat source at depth. It just has not been found. Each individual part of the system, where, for example, the fluids ascend and so on, that can be controlled by local faults and so on. So that is sort of superimposed on this magmatic origin of of the heat. But I'm probably the wrong person to ask about because that's a very different the actual geothermal operations where people drill and so on. That there's also a lot of confidential information. You may not actually know all of this. It's proprietary by the geothermal operators. The sketch maybe shows you a little bit of sort of the where they have this this fractured and permeable rock. It's very complex because there's been a lot of faulting in this region, and there's certain parts of the system that are more productive than others. And just as an aside, over the initial 20 to 30 years of geothermal fluid production in the geysers, people have noticed that actually the vapor pressure decreased. The system was being depleted, and in order to reactivate the system, the geothermal companies built a pipeline from the city of Santa Rosa. It's about 50 kilometers away from the geothermal field, and they take sewage from Santa Rosa and pump it into the system and reheat it again, and that increased the steam production. So they actually were able to counter the depletion of the steam. So they turned shit into steam.
Yes, my question is, so should we actually rethink the representation of the geological age, in particular pluton? So the plus minus, it's not only analytical uncertainty, but also it includes the lifetime of the system. And maybe younger it is, more significant it is, so maybe older it is, maybe it's a little bit less significant. But should we actually realize that it's not only analytical uncertainty, but it's also lifetime? So I think this should be really emphasized for like the future.
I think so, yeah. I would subscribe to exactly this point. If you're dating a Pluton that's 2.5 billion years old, that's within the noise. But nonetheless, the standard that you use, for this may be a Proterozoic standard, and then you start thinking about, okay, how well can we actually date this, or what is a reasonable geological uncertainty? Because the measurement uncertainty can be much smaller, but it may not be significant because it reflects, a natural way zircon crystallizes may be much longer than what we can actually.
Yes, it's actually one of the main conclusions from this study. It's not that this plus minus, so we have to really determine which age is most accurate, so we can take as geological age one. And this plus minus also included such a history, not only analytical.
Yeah. Yeah. I don't know if I may have time or.
Yeah, go for it.
I don't want to keep you too long. Yeah, just for fun, I did basically this exercise and took this young zircon, this quaternary zircon, and pretended it's 50 million years old. If we take a zircon that is old in the middle and it has a range of uranium-lead ages similar to here, so they can be up to 2 million years older, and they're actually a couple of real phenocrysts as well. That's about 15 million years. And we take this zircon and then 50 million years, the same volcanic system, and we do the high precision work that we can do with TIMS. The data would look something like that. This would be the range of zircon age that we would get. The actual, the last crystallization event would be here. None of the analyses would overlap with this. And if you would look at this data, you would probably say, oh, there's a little bit of lead loss here. This is the bulk of the data. And then there's maybe a little bit of inheritance. So it's 50.5 million years old. But in fact, and that's not wrong. In some extent, there is older parts of the zircon. But the latest event is actually 50 million years.
Yeah, maybe it's applicable to other systems as well.
Yeah.
One last quick question, if there are any.
Again, you're talking about the late stages of high-level plutons, recharge and eruption. But can you take the whole mode of thinking further back? No one in WA likes a young rock, and everyone loves a xenocrest. Can you go look at a xenocrest and use the same mode of thinking and start talking about what rocks melted first, and then a bit later, when packets of melt started to assemble into a body of magma that then became mobile, the generation of the plutons at a respectively old age.
Yeah, if we can really resolve that, for these very old ages, I think that would be one limitation here, because that's the lifetime of a magmatic system, an arc or so is still, limited to 10 million years or something like that. So if it's a xenocrest that is much older, then it may be completely unrelated, its geological history to the actual younger magmatic event, and that then makes it more difficult to tie these processes together.
But no one's had a crack at doing such a thing.
I mean, people of course look at the chemistry of the xenocrysts, what is the provenance and what are the sources. That you can definitely do. With regard to the time information, that is then, to directly use it to say something about magma processes, that's maybe a little bit too difficult.
That's a problem resolution.
Yeah, yeah.